Welcome to the lecture number 14 of Theory of Computation. In this lecture, we will go through pumping lemma for regular languages, then application of pumping lemma. In the last class, we have gone through what is the Chomsky classification of languages, and in that we have studied one type of language that is called as type 3 language or regular language. Then today we will go through one lemma for that one and one application of that pumping lemma. So before going through that, let me give you a motivation. Suppose there are a pigeons. Okay, suppose there are n number of pigeons. N number of pigeons. And suppose there are m number of holes. M number of holes. So pigeon number or hole number 1, hole number 2, dot dot dot, hole number m. Now if m equal to n, and if I will put the restriction that all the pigeons should be placed in a distinct hole. So here one number pigeon will be inserted in one number hole, two number pigeon will be inserted into two number hole. Similarly, n number pigeon will be inserted into m number hole. So now if I will put another restriction, if number of pigeons n is more than the number of holes m, so it means what? There will be at least one hole where you will have multiple pigeons. For example, if n equal to, let's say n equal to 5 and m equal to 3. Okay, so 3 holes are there and 5 pigeons are there. So what you will do? So m equal to 3. So now in this hole you will put a pigeon. In this hole you will put a pigeon. In this hole you will put a pigeon. Now you see there are two more pigeons that need to be inserted into the holes. So here you see as n is greater than m, here you will see there will be at least one hole where the number of pigeons is more than 1. Okay. So based on this principle, this lemma has been developed. So what is the lemma? So let m be a finite automation. So finite automation means it can be defined by 5 tuples. One is q, number of states, input alphabet, delta is a transition function, u0 is the initial state, and f be the set of final states. So let m be a finite automation with n states. So in this finite automation, how many states are there? N number of states are there. Okay, so let L be a regular set. Regular set means let L be a language that contains a set of strings which is accepted by M, and let W be a string which is an element of the language L, means it's any string element of the language L, if mod W is greater than equal to M. Mod W means what? Length of the string. So if length of the string is greater than equal to m, and if m is greater than n, means number of symbols in the string is greater than or equal to the number of states, then we can split the string into x, y, z such that w equal to xyz, w equal to x, y, z, with y not equals to epsilon, this or this epsilon, and there exists a string x y to the power I, z, which belongs to the language L for each I greater than equal to 0. So let me explain you this one again. Suppose let me take a finite automation. So this is a finite automation. U0, by taking 0 as input, it goes to Q1. By taking 1 as input, it goes to, let's say, Q2, which is the final state. So here how many number of states are there? There are 3 number of states. So n equal to 3. So now let me take a string 0, 0, 1, 1. So now if I will take, or 3 zeros, 0, 0, 0, 1. Okay. So if I will take this string, so here w equal to what? W equal to 0, 0, 0, 1. So what is the length of w? It's nothing but 4. Let's say it is greater than equal to m. Let me take m equal to 4 again. So 4 is greater than equal to 4, no problem. So then what I will do, I can define it in terms of x, y, z, w equal to x, y, z, where x equal to 0, let me take x equal to 0, z equal to 1, and let me take y equal to 0, 0, or let me take y equal to single 0. Okay, so here what I can do, I can define the w in terms of what? X, y to the power I, z. X, y to the power I, z means x is 0. Let me consider y as a single 0. So here I will do 0 to the power 2 and z equal to 1. So now you see what you will get, w equal to x, w equal to x, this is x, y to the power I means 0 to the power 2, z equal to 1. So it means what? There will be at least a self loop over here. Okay, so q, by taking 0 it goes to q1. Here it can take any number of zeros. Then finally when it gets a 1, it goes to the final state. So for every y, or for every I greater than equal to 0, that string should be accepted by that finite automata. So if that is accepted by the finite automata, it means what? It is a regular language. So here one interesting thing you can see, that if P0 is the initial state and this is the final state, and let this subset of this substring represent x, and let this substrings represent z, then there will be a self loop which will represent y. So here every string longer than the number of states must cause a state to repeat. So if the number of states, or if the string length is more than the number of states, then there should be at least one self loop. Okay, it is exactly like to the pigeonhole principle. You see, if there are n number of pigeons and m number of holes, if n is greater than m, there should be at least one hole which contains more than one pigeon. So similarly to here, if a string is longer than the number of states, then in that state there should be at least one loop which will repeat. Okay, so this is nothing but the pumping lemma for regular languages. So now what is its application? Its application is this theorem can be used to prove certain sets are regular or not. It means what? If I will write a to the power n greater than equal to 0 is regular or not, it can be checked by using the pumping lemma. So how can you check? So there are basically three steps. So I hope all of you are studying discrete mathematics. In discrete mathematics, there is a proof technique that is called as proof by contradiction. So in proof by contradiction, what we will do? Suppose I want to prove I am an elephant. So for that, what you will do? First, I will assume that I am an elephant. Now, what I will do? I will check whether elephant has two eyes. Yes, I am having two eyes. Whether elephant has two legs? No, elephant doesn't have two legs. Elephant has four legs. So it means that I am not an elephant. So if proof by contradiction, what we will do? First we will assume that it is true, I am an elephant. Then I will prove that there is some element in the elephant which is not present in me, therefore I am not an elephant. Okay, so this is the proof by contradiction technique. So now here you see, here what we will do in step number 1, we will assume that L is regular. So first we will assume that L is regular. Then let n be the number of states in the finite automata. Okay. In step number 2, what we will do? We will choose a string w such that the length of w is greater than the number of states. So using pumping lemma, what I will do? We will split the string into three parts, x, y, z, such that mod of xy is less than equal to n, and y should be mod of y should be greater than 0. So next what we will do? We will represent w equal to x, y to the power I and z. Then we will choose a suitable integer I such that x, y to the power I, z does not belong to the language L. Then what we will say? That it means that this language is not a regular language. So first we will assume that this is a regular language. Then we will split the string into x, y, z. Then we will choose a suitable I such that we will represent the w equal to x y to the power I z. Then we will choose a string such that it will not be generated by x y to the power I z. Then we will say that that is not a regular language. So let me prove this one by help of one example. Okay. So here let me show that the language L equal to a to the power n, where n is greater than equal to 0, is regular or not. So in step number 1, what I will say, what I will do in step number 1, I will assume that, so assume L is regular. So I have assumed that L is regular. In step number 2, what I will do, here you see in step number 2 what I will do, we will choose a string w. Okay, so here let me choose a string w equal to a. Okay, such that you see the number, it should be more than the number of states. So here let the number of states n equal to 1. So here I have taken a string which contains the number of symbols which is more than the number of states. So now what I will do, I will make it as, or I have told you w equal to x y z. So here you see I will take, let me take x as epsilon, z as epsilon, and let me take y as a. Let me take y as a. Now what I will do in step number 3, so you can take any string. Okay, you can take any string, but that should satisfy this condition. Mod of xy should be less than equal to n, and mod of y should be greater than equal to 0, greater than 0. So now in step number 3, what I will do, I will choose a suitable I. So you see in step number 3, find a suitable integer I such that x y to the power I z does not belong to L. So here I will choose w equal to so x is what, epsilon, y is what, a to the power I, z is what, z is epsilon. Now when I equal to 1, so when I equal to 1, then what I will get, I will get w equal to epsilon a to the power 1 means a epsilon. So what I will get, a. Now you check whether a is a string of this language or not. So what is the language? L equal to a to the power n. So what is a to the power n? N greater than equal to 0 means when n equal to 0 it's epsilon, when n equal to 1 it's a, when n equal to 2 a to the power 2 it's a, n equal to 3 it's a, n equal to 4 it's a. Now it will go on like this. Okay, so now you see when I equal to 1, I have to choose a suitable I in such a manner that that should not belong to the language. So I equal to 1, so what I have got, a. So now you see a is an element of the language. Now I equal to 2, so I equal to 2, what I will get, w equal to epsilon a to the power 2, a to the power 2, what I will get, a epsilon. It means I will get a. Now I equal to 3, so w what I will get, epsilon I to the power 3 means a to the power 3, sorry. So you will get a epsilon. So what you will get, you will get a. So now you see this is again is an element of this language L. So it means what, for all I or for each I greater than equal to 0, the string generated by x w equal to x y to the power I z belong to the language. It means what? It means this language L equal to a to the power n greater than equal to 0 is a regular language. So if I will be able to generate such a string which is not present in L, then I can say that that is not a regular language. Okay, but as it is, as all the strings generated by x y to the power I z belongs to this language, so I can say that this is a regular language. So let me go through another example. Here L equal to a to the power 2n for n is greater than equal to 0. So which strings will be there in the language? Put n equal to 0. So a to the power 2 into 0 means epsilon. A to the power 2 into 1. So what you will get? AA. A to the power 2 into 2. What you will get? 4a. A to the power 3. 2 into 3. 6. So 6a. You will get like this. Dot 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 like this. Now you see in step number 1 what we will assume? In step number 1 we will assume that L is regular. Regular. Now we will go through step number 2. So in step number 2 what we will choose? We will split or we will choose a string W. Let me choose the string W equal to A. Okay. So here W equal to what do we have to choose? X, Y, I, Z. So let me again tell or let me again take X equal to epsilon, Y equal to AA and Z equal to epsilon. I can choose, there is absolutely no problem, you can take anything, okay, but that should satisfy the condition mod xy less than equal to n and mod a and y should not be equal to epsilon. Okay, so now in this case what we will do, we will go through the step number 3. So in step number 3 what we will do, we will take w equal to x y to the power I z. So we will generate the strings by taking multiple I. So first I will take I equal to 1, then I equal to 2, then I equal to 3 like this. Okay. So first let me take I equal to 1. So in I equal to 1 what I will get, W equal to, so what I will get W equal to, so W equal to I will get epsilon a epsilon, right? So I will get a. Now I equal to 2. What I will get? W equal to epsilon a. So here y equal to a. Okay. So a to the power 2 I will get 4a epsilon. So what I will get? A. I equal to 3. What I will get? W equals to a. So you see for each I what I am generating that is present in the language L. Okay, so it means all the strings that will be generated by pumping this y to the power I, that will be in the language L. It means what? It means L is regular. So if I will be able to generate such a string which is not present in L, then I can prove that L is not regular. Okay, okay, let me go through another example, okay, where I will prove that that language is not regular. Okay, so here let me show that a to the power p, where p is a prime number, is regular or not. Okay, so what is the language accepted by this? So L equal to prime means 2, 3, 5, 7. So here you will get a is a prime number string a to the power p. Okay, so a. Next a. Similarly a to the power 7, it will go like this. Okay, so now you see here in step number 1, in step number 1 what I will assume, I will assume L is regular. I will assume L is regular. In step number 2 what I will do, in step number 2 I will choose a string W such that x y, I will split the string W, which is, it will be split into x y z in such a manner that mod of xy should be less than equal to n and mod of y should be greater than 0. So here let me choose W equal to, let me choose a string W equal to x equal to epsilon, y equal to, let me take a, same thing, z equal to epsilon. Okay, x equal to epsilon, z equal to epsilon, y equal to a. Now let me use the pumping lemma. So step number 3. So in step number 3 what I will do, I will choose this or I will generate a string W in such a manner that that is not there in the language L. So x y to the power I z. So x is what? Epsilon. So now let me put I equal to 1. So what W I will get? W equal to x is epsilon, y to the power 1. What is y? Y is a. So a to the power 1 is a. What is Z? Z is epsilon. So what I have got? I have got A. Now you see A is present in the language. So there is absolutely no problem. Now let me check I equal to 2. So what W I will get? Which string I will get? Epsilon y to the power 2. Y is what? A. So A to the power 2 is A epsilon. So which string I have got? A. Now you see, four A's are not present in this language. It means what? It means the L equal to A to the power P, where P is a prime number, is not regular, because all the strings that I will generate by making y to the power I for I is greater than 0, that are not present in this language. It means this language is not regular. So if all the strings are present, then that is a regular language. Okay. So I hope all of you have understood the application of pumping lemma. Thank you.